So here we are in section 5.4, projections in Hilbert space isomorphisms. So what we'll do in this section is drag a bunch of ideas from Rn into Hilbert spaces. A specific kind of Hilbert spaces, there'll be infinite dimensional separable Hilbert spaces, that is, infinite dimensional Hilbert spaces with a Schauder basis. And we'll see finally the long-awaited fundamental theorem of infinite dimensional vector spaces to show that every such Hilbert space is actually isomorphic to little L2. So we'll start with projections. Since we have inner products in Hilbert spaces, then we can use those inner products the same way you did in linear algebra to define projections. Dig through your old linear algebra notes, see how you projected one vector on another. We're doing the same thing here, except we don't use dot product notation, we use inner products. So in an inner product space, we define the projection of F onto non-zero vector G in a Hilbert space as projection of F onto G is the inner product of F with G divided by the inner product of G with itself times vector G. So we see very much a magnitude and direction thing. We're looking in the direction G by having vector G there. The magnitude is determined by these various inner products. Of course, we could tweak this in the denominator. If I can write this in terms of the norm induced by the inner product, we could write that denominator as the norm squared of G. If we had G as a unit vector, then that would simplify things, and we'll do that, and that's why we'll look at orthonormal sets ultimately. So here's how we define the projection of one vector onto another. We'll eventually project vectors onto subspaces, but for now, for a non-empty set S in a Hilbert space H, we say that vector H is orthogonal to S if the inner product of H with S is 0 for all vectors in that set. We'll consider such sets, and oftentimes they'll be subspaces instead of simply sets, so they have a little bit more structure, but we're dealing with this in a general setting, as we're prone to do. The orthogonal complement of a set, this is pronounced S perp, as mentioned below. Sometimes it's called a perp space of set S. S perp is defined to be all vectors H in the Hilbert space such that the inner product of H with S equals 0 for all S in set capital S. In other words, it's a collection of all vectors in the Hilbert space that are all orthogonal to all the elements of set S. So simply a set of vectors, by definition, we can go beyond that and actually show that if we start with Hilbert space H, then this S perp thing itself is a Hilbert space. And that's theorem 5.1.4. Sorry, 5.4.1. Let's look at a proof of that. Okay, S perp is a vector space. That is, it's closed under linear combinations. If I take a linear combinations of vectors orthogonal to all the elements of set S, that linear combination itself will be orthogonal to all vectors in set S, follows from the linearity and conjugate linearity of inner products. So that part we'll just take as given. And all we need to show is the completeness stuff. So we're claiming that S perp is a Hilbert space. We know it's a linear space. We know it has a norm on it, the same norm as the big space. Completeness is a concern. So let S sub n be a Cauchy sequence in S perp. Then H is complete. So this Cauchy sequence S sub n converges to something in H. Call it lowercase vector, vector H, lowercase h. That is, we'll have the limit as n approaches infinity of S sub n, the terms in that Cauchy sequence, to equal this vector H, based on the completeness of H. Now we need to see if H itself is actually in S perp, and it is, and it follows by continuity of the inner product. The inner product of H with S, well, H we've written is a limit of the S sub n, so we'll just substitute in there. We can bring limits outside of inner products. In other words, the inner product is a continuous procedure, as is to be shown in section 5.2, exercise 6. If these notes are being used as supplements to the Promislow book on functional analysis, then it's explicitly shown in that collection of notes that inner products are continuous. But then the inner product of S sub n with S, those are always zeros. The S sub n's were chosen to be from S perp, so they're perpendicular to this vector S, an arbitrary vector in set capital S. All these inner products are zero, so the limit's zero. That is, the inner product of H with S is zero. That being the case for all vectors S in set capital S implies H is in S perp. And so this Cauchy sequence converges to H, an element of S perp. Arbitrary Cauchy sequence in S perp converges to an element of S perp. That's completeness. So S perp really is a complete normed linear space. I'm sorry, a complete inner product space. That is, it's a Hilbert space. Back to the notes. Okay, I'm going to use this idea of orthogonal complement to decompose a Hilbert space into subspaces that are orthogonal to each other, somewhat in the sense of the perp space just described above. As we'll see, this decomposition, it's an algebraic decomposition, not a set theoretic decomposition, so we don't get the term decomposition used in a set theoretic way. There will be two sets of vectors, and it won't be the case that these sets of vectors themselves form a set theoretic decomposition of the Hilbert space. It'll involve the vector addition idea. Theorem 5.4.2 says, let S be a subspace. Okay, so we're taking a little bit more than a subset. I told you so. We'll use this S perp idea, which was valid for any set. So it's valid for subspaces. Those form sets of vectors too. So we'll take S to be a subspace of a Hilbert space H. Claim is, for any vector H in the Hilbert space, there exists a unique T in S such that the infimum as vectors S range over subspace capital S, norm of H minus S equals the norm of H minus T. In other words, when we consider this infimum for a given H as S ranges over all vectors in that subspace, that infimum is attained, that minimum, we could say, is attained, and it's attained at vector T, some unique vector in subspace S. In other settings, in the Promislow book I mentioned earlier, for example, T would be called the vector in set S that is closest to H. And we'd associate this as a distance between vector H and set capital S. And I think the Promislow notes and video includes a proof of this. We'll go through proof again. Same proof, I suspect. Okay, so we'll define D to be that infimum. Norm of H minus S as S ranges over subspace, capital S. And we'll choose a sequence, S sub n, of elements of S, such that the limit as n approaches infinity of the norm of H minus S sub n equals D. You can do that because D is defined as an infimum. So we can find a sequence of S sub n's such that in the limit, that sequence takes this value to that infimum value. Properties of infimums. So we've written the distance in terms of this limit. Then in that sequence, notice if we take S sub m minus S sub n, norm squared, that can be written as S sub m minus h minus the quantity S sub n minus h. The minus h is canceled, so you can't argue with that arithmetic. And we'll take a norm and square it, and then deal with this in terms of the parallelogram law, which is stated in section 5.2 as one of the exercises. It states that in a parallelogram, determined by vectors in this setting, but it's a classical result from Euclidean geometry. For parallelogram, the sums of the squares of the diagonals equals the sums of the squares of the four sides. And we could put geometric interpretation on these things. Here's a side squared, here's another side squared. Well, it's a parallelogram, so it's got four sides. That's where the twos come from. This is one diagonal, and this is the other diagonal to give it a geometric flavor. But the parallelogram law allows us to deduce this. The sides of that parallelogram are determined by the norms of the differences here, the S sub m minus h and the S sub n minus h. But that allows us to produce this equality. Now, let's factor a 2 out of this. It'll come outside of the squaring as a 4 and outside of the norm. Maybe it's easier to see backwards. Let's take this 4, put it back inside that norm. It'll go inside as a 2 because of the square up here. We'll get a 2 inside. That'll produce a 2h. Why, there's a 2h right there. And that'll get rid of this 1/2 and yield this sum. And there's the sum right there. It's actually a negative sign difference between these two statements otherwise, but not a problem since it's all inside a norm. So we get this equality here. Now, here we have the norm of h minus an element of S. Remember, S was a subspace. S sub n and S sub m are elements of S. So 1/2 S sub n plus S sub n, this is an element of S. And we've got something of the form norm of H minus an element of S. But the infimum of the norm of H minus an element of S is D. So whatever this is, it's greater than or equal to D. This is greater than or equal to the infimum up here, where we might replace S with this vector here. This greater than or equal to D. We got a negative sign in front, so we'll reverse that inequality and say negative this is less than or equal to negative D. We got a power of 2 there, so we pick up a power of 2 there, producing this. Okay, not a surprise. Probably going for Cauchy here, given what we've considered, a sequence, and we've looked at S sub n minus S sub m, difference of terms of that sequence. What? The S sub n's satisfy the condition that the limit as n approaches infinity of the norm of H minus S sub n equals D. So when n is big, this is close to D. The norm is close to D. Okay, we're off by negative sign again, but not a problem. Similarly over here, if m is sufficiently large, then this is close to D. Since this limit equals D, without getting into too much with the epsilons and deltas, this can be made close to D. This can be made close to D, the norms. In so doing, these first two terms get close to 4D squared. And then we subtract away 4D squared. So what we're doing is, for m and n sufficiently large, if you like epsilons, we could go through and put an epsilon n argument together, capital N, dealing with sequences, and show that this can be made as small as you want and positive. In the limit, we'd get out a 0, but that means we can make the distance from S sub n to S sub n, the norm of the difference, we can make that as small as you'd like, positive, by making the indices sufficiently large. In other words, that's a Cauchy sequence. All right, so this and this get close to D, so the right-hand side gets close to 0. And that's what we're saying up here. The limit is D, so that right-hand side can be made close to 0. And we see that the norm of S sub m minus S sub n approaches 0 for m and n sufficiently large. So we really are dealing with this sequence S sub n, the Cauchy sequence. Cauchy sequences are convergent. We're in Hilbert spaces. say that Cauchy sequence converges to some T sub 1 in S. S was a subspace of the Hilbert space and itself was taken to be complete. So there's a T1 in S that such that the limit as H, the limit of the norm of H minus S sub n equals a norm of H minus T sub 1. So we found the existence of a T sub 1 in S where that infimum is attained. This limit was also D, and D was the infimum. So there's a lot of symbols around, but there's a T1 in S that is closest to H, if you want to speak of it in those terms. We said there's a unique such element of S. So we found the existence of one. For uniqueness, suppose there's a second one. Suppose we also have the limit as n approaches infinity, the norm of H minus S sub n equal to the norm of H minus T sub 2. Now, there may be plenty of vectors out there in the Hilbert space that might satisfy something like this, but here we're taking the T1s and T2s to come from a particular place. They're coming from set S. So limits of the norms are the same. T1 and T2 are both elements of S satisfying this limit condition. Let's look at the norm of T1 minus T2, norm squared. Parallelogram law again, so same type of argument we had above, except this time using the T1 minus T2 instead of, I think we had S sub m minus S sub n on the previous slide, but same type of argument. Here, we've actually assumed that these norms equal D, equal the limit value. So both of these equal D, that gives us a 2D squared plus 2D squared, that's 4D squared. Over here, parallelogram law has produced this. Here we have H minus, well, that's an element of S, isn't it? Yeah, it's a linear combination of T1 and T2. T1 and T2 are from capital S, and capital S was a subspace. So yeah, this is an element of S. So when we take the infimum over all elements of set capital S, H minus those vectors, that infimum must be less than or equal to H minus this particular vector in set S. And so we draw the conclusion that this quantity, the norm part is greater than or equal to D. So what we would do then is introduce a negative to reverse that inequality because of the negative out front. Making the substitution, we'd get that this is less than or equal to 4D squared minus 4D squared. This is less than or equal to 0. Well, it's a norm squared, so it ain't less than 0. So it must be that this quantity equals 0, the norm of T1 minus T2 equals 0, and so T1 equals T2, and there's your uniqueness. So there exists only one element of T element of set S that's closest to vector H. All right, I said set S, I need subspace, actually. Really what we need is closure under vector addition. This can be slightly weakened. It is in the Promise Low book, but we'll just take it to be a subspace because that's how we're going to use it. Now, that nearest vector allows us to do a kind of decomposition of the elements of H into an element of a subspace S and the perp space to that subspace. As stated in Theorem 5.4.3, and all this perp stuff, there's got to be geometry behind this. I'll try to describe that a little bit. Theorem 5.4.3 says, let S be a subspace of a Hilbert space H. For all vectors H in the Hilbert space, there exists a unique decomposition of the form H equals S plus S prime, where S, lowercase s, is in subspace S, and little lowercase s prime is an element of the perp space of set S, of subspace S. All right, so you might think in 3 dimensions, this is legitimate in 3 dimensions, Of course, we're going well beyond that. I might have a vector in 3 dimensions, and we might have as a subspace a collection of vectors that form, the xy plane when put in standard position. And I got a vector maybe that's in standard position that emanates from the origin, and it's got a vertical component to it. Well, then I can take that vector and write it as a horizontal component. That would be something related to the xy plane, a vector that lies in the xy plane when put in standard position, plus a vertical component. So it kind of breaks down like that in its most elementary use. So there's geometry there, as promised. And let's go through the proof. And the proof will use this nearest vector thing that we had from Theorem 5.4.2. So for H, a vector in the Hilbert space, let T be in set S as defined and guaranteed to exist and to be unique by Theorem 5.4.2. So this is the vector in S such that the norm of H minus T was minimal over all elements of subspace S. So that's how we define that. So we've picked this T that's really the vector in set S, subspace S, nearest to H. We'll define R to be H minus T. Rearranging this, we get H equals R plus T. T's in the right place, it's in S. If we can show R is in the right place in S perp, then we're done. So we'll take T in S, capital S, to be the lowercase s vector here. And we want to take R to be, or take S prime to be the vector R, provided it's in S perp. And we'll have exactly what we want, an element of capital S plus an element of capital S perp. Well, we got no problems. We know T is in S. We need to show that this R vector, so defined, is in S perp. So we need to show it's perpendicular to everything in S. So take an arbitrary vector in subspace S, call it S sub 1. Let A be any scalar. The norm squared of R, we define R to be H minus T. That'd be the norm squared of H minus T. That's less than or equal to H minus the vector T plus AS sub 1. Why is that? Because this norm is minimized by taking H minus an element of set S. That minimum is reached with vector T. That's what we showed in the previous theorem. Here's another vector in set S. Hey, T was in S, right? S sub 1 is in S, right? We picked it that way. So in parentheses, there's another vector in set S. Well, the minimum of the norm over all such vectors in set S is attained there. So here we get a greater than or equal to because that's a vector in set subspace, capital S. H minus T, I see, hey, H minus T is R, so let's make that substitution. Distribution here, you get a negative sign there. We want the norm squared of this vector. Let's go back and write it in terms of inner products. In the Hilbert space, in the inner product space, that norm is determined by taking the inner product of that vector with itself. So inner product of R minus AS1 with itself. Expand this out using the linearity properties and definitions of norms induced by inner products. And this will produce, as we've done several times before, we get the inner product of R with itself, that is the norm of R squared. We get what I kind of call a cross terms. And then we get the inner product of the last vector with itself, producing a norm squared of S sub 1, and we can bring the scalar outside of that as an absolute value, or modulus, because we're dealing with complex inner products, which is about to play a role. So what we have here is subtract this from both sides, cross out the norm of vector R squared. We've got a situation where 0 is less than or equal to this part of the right-hand side. Let's write this first. That is, 0 is less than or equal to the modulus of a squared times the norm of s sub 1 squared minus these two inner products. That's exactly these last three terms, simply rearranged and canceling the norms of r squared from both sides. Okay, this is valid for any scalar a. Now we're about to pick some specific scalars. Well, the formula that we've got here, it's good for any scalar. We're going to apply it to specific scalars. Remember, we're trying to show orthogonality. We're trying to show that R is in S-perp, that R is orthogonal to everything in set S. We've chosen an arbitrary element of set S, this S sub 1. We're trying to show, we're trying to show this inner product is 0. The inner product of R with S1 is 0. We're going to do it by having to consider the real parts and the imaginary parts. So we left off with this inequality. If the inner product's complex valued, and that's our setting, and we take A to be real, we can do that. A could be any scalar, including a real scalar. Then what we'd have from this would be, notice the order's different on these two, so that would introduce a conjugate. We factor a negative out, we'd have a sum of a complex number and its conjugate. That produces twice the real part of that complex conjugate. So we'll get twice the real part of the inner product of R with S1. Scalar A has come out as a coefficient. Okay, the 2 comes from the fact that a complex number plus its conjugate is twice the real part. So that's where the 2 and the real part came from. A is brought outside of both of these, and it's real, so I don't have to worry about that conjugate stuff. Producing this. Okay, let's add another restriction. Let's take A as real. This only holds if A is real. This previous line, that holds for any scalar. Here we've assumed A is real. Now let's also assume A is real and positive. If A is real and positive, then we could take this to the other side of the equation. We'd have 2 times A times the real part of the inner product is less than or equal to this thing. We could cancel the A's out. Divide both sides by A. Doesn't change anything. We've assumed A is positive. It leaves the inequality the same. Then we would have 2 times the real part of the inner product is less than or equal to A to the first power times this quantity, the norm of S sub 1 squared. Then let A approach 0. Right-hand side will approach 0. There will be a factor of A here. This approaches 0, and we'll draw the conclusion that 2 times the real part of the inner product is less than or equal to 0. Or in other words, the real part of the inner product is less than or equal to 0. Again, assuming A is positive, and then taking a limit as A approaches 0. If A were negative, we'd do a similar type thing. Take this to the other side, divide both sides by A. A's negative, that'll reverse the inequality. Same argument. You'll reverse the inequality in the argument as well, and you'll get that the real part of the inner product is greater than or equal to 0. Well, the only way you can have the real part less than or equal to 0 and greater than or equal to 0 is if the real part is 0. Let's repeat that argument again on the imaginary part. So going back to the equation, the inequality that holds for any real number, A, any scalar, any complex number, A. We were taking the scalars to be complex. And let's take A to be a purely imaginary number. Say A equals IB, where B is a real number. So purely imaginary, it's some real multiple of the I parameter, square root of -1 if you like. Here's the inequality we had, except we've replaced A with IB. So we've made that replacement. We had an absolute value out here, so we've picked up simply B squared. B itself is real. Here's the IBs that have appeared inside those inner products. Now, using the conjugate linearity, we'll bring the I out. That affects a sign here, doesn't affect a sign in the second component. We'll bring the B's out as well. And here you've got an inner product of S1 with R and an inner product of R with S1. Well, we put a conjugate on, let's put a conjugate on the second one, put a conjugate on this, reverse the order, using the properties of complex valued inner products. Then you bring the IB out, then you have a complex number minus its conjugate. When you have a complex number minus its conjugate, you get 2i times the imaginary part of that complex number, property of complex numbers, elementary property of complex numbers. So this minus its own conjugate, reverse the order, put in a conjugate, yields 2i imaginary part of the inner product. Okay, got an I here and here, that'll produce a negative out front. We've got the 2 here, the B here, the imaginary part of the inner product. And it's the same argument we had on the previous page. Now, let's take this, move the 2B imaginary part of the inner product, move that to the other side of the equation as discussed, but never blatantly written on the previous slide, and do the same kind of thing. Divide the B's out. Okay, if B is positive, so now we'll assume B is positive. That doesn't reverse the inequality. Then we've got a B on this side and not on that side after simplifying. Let B approach 0. This term goes to 0, so 0 must be greater than or equal to the imaginary part. Take B to be real and negative. Then when you divide the B's out, the inequality is reversed. Then you get 0 is less than or equal to the imaginary part by taking some limits. And same argument as before, we deduce that the imaginary part of the inner product equals 0. So we've shown the real and imaginary parts of the inner product are both 0, so the inner product itself is 0. We were trying to show what? We're trying to show R was an S perp. We just did. We just showed that the inner product of R with S1 is 0, where S1 is an arbitrary element of set S. In other words, R is an element of S perp. And then we have written H as H equals T plus R. T we had from the previous theorem. R we now have to be an element of S perp. So that gives a representation of an arbitrary H in the Hilbert space in terms of an element of S and an element of S perp. Is it unique? Well, suppose H equals T1 plus R1 and it equals T2 plus R2, where the T's are from S and the R's are from S perp. That is, suppose these are two different ways of representing H as a linear combination of an element of S and S perp. We can take this equation, bring the T's to one side, the R's to the other. That yields T1 minus T2 equals R2 minus R1. So the indices are in the opposite order, but that's correct. But T1 and T2 are in subspace S. So T1 minus T2 is in subspace S. R1 and R2 are in S perp, which we saw to be a subspace itself. And so R2 minus R1 is also in S perp. But they're equal to each other. The only thing that occurs in both a set or subspace and its perp space is the 0 vector. Easy to confirm that. So it must be that these T1 minus T2 and R1 minus, or R2 minus R1, this must equal 0 since it's common to both S and S perp. In other words, T1 equals T2, R1 equals R2, and there's a uniqueness. So every vector in the Hilbert space can be uniquely represented as an element of S plus an element of S perp. This we use to define projection. So we're defining projections using these decompositions, and these decompositions are based on this infimum that we introduced somewhere upstairs. It's based on this idea here. which is commonly termed the distance from set S to vector H. So we found these nearest vectors when we were dealing with subspaces, and that's how we'll define projection. That's not very hands-on. It'd be a little cleaner if we could do this in terms of inner products, and we will before it's over with. We'll see the Gram-Schmidt process before it's over. So, excuse me. For H, a vector in a Hilbert space, the vector S described above, where we had written H is S plus S prime in terms of the subspace and the perp space. This vector S is called the projection of vector H onto subspace S, represented as given here. It's the projection of vector H onto subspace capital S equals lowercase s. I read it carefully to distinguish between the fonts. It's hard to tell when there's sometimes subscripts and sometimes not. We also say that H can be written as the direct sum of S and S perp, denoted H equals S direct sum S perp, and that H has an orthogonal decomposition. We've written H, I want to say we partitioned H into this set and this perp set, but that's not true because there's elements of H that are in neither of these, but every element of H is either in S perp, or is a linear combination of an element of S and an element of S perp in this sense. So that's what this orthogonal decomposition stuff is about, is writing vectors in that form. A set of vectors, set of non-zero vectors, is said to be orthogonal if the vectors are pairwise orthogonal. That is, you take two different vectors and their inner product is 0. If in addition each of the vectors is a unit vector, then it's called an orthonormal set. Your favorite kind of bases for vector spaces are orthonormal bases. All right, well, let's see if we can't find us some orthonormal bases for Hilbert spaces. Probably want them to be countable, and I want to interpret linear combination in the sense of Schauder, infinite linear combinations. I want that to be on the table in this particular reference. So a Schauder basis of a Hilbert space, which is also an orthonormal basis, also an orthonormal set, is called an orthonormal basis or a Riesz basis. This term orthonormal basis in the other reference in the Promislow book, often used in functional analysis, they define things subtly different when they talk about orthonormal bases. I mean, I can save this by saying Riesz basis. They don't mention Riesz bases. But when we talk about a Schauder basis, that means you're allowing infinite linear combinations. Series. You're writing everything in the vector space as a series of elements in the countable Schauder basis. So a Schauder basis that's orthonormal, we'll call an orthonormal basis, and probably stick to that terminology. I need to be clear in this setting of Schauder that we're taking infinite linear combinations. That's the thing that's changed over Rn and over sophomore linear algebra. Okay. Theorem 5.4.4 actually is probably pretty familiar to you from sophomore linear algebra. It says a Hilbert space with a Schauder basis has an orthonormal basis. So you can take that Schauder basis and convert it into an orthonormal basis. How so? Gram-Schmidt process does that. You do the Gram-Schmidt process in Rn, and you convert an ugly basis into a pretty orthonormal basis. Well, let's do that. Schauder basis, well, a Schauder basis is a countable basis. So we'll start with a Schauder basis, and we'll construct an orthonormal basis from it, the same way you do in sophomore linear algebra. One of the little details is left as an exercise in this, but the manipulations are the same thing as sophomore linear algebra. First, we'll define vector R1 to be vector S1 normalized. So I really want to think of vectors as magnitude and direction. And it turns out I can successfully if we have a Schauder basis. So we're kind of thinking of these different directions. they're nice orthonormal directions when we get done creating this orthonormal basis. But direction S1 is represented by vector R1. It's a unit vector. You know, we want it orthonormal, so we got to normalize as we go. Now let's move on to vector S2. It might have a component in the direction of S1. If it does, subtract that component away. That'd leave you with a new vector that is perpendicular to S1. Oh, excellent. And then normalize it. So what we'll do for k greater than or equal to 2 is define the span of a bunch of vectors, R1, R2, up to R sub k minus 1. So we have a basis for this space, R sub k. The R's will be orthonormal vectors. We're inductively creating them as such. Notice this gives us R1 through R sub k minus 1. We'll define R sub k by taking the kth vector in this set, subtracting off the projection onto the span of the previous vectors, keeping a fundamentally new direction, and then normalize it. And that's how you create an orthonormal basis from a regular basis that may not be orthonormal. That's the Gram-Schmidt process. The inner product is easy enough to see. If I take the inner product of R sub I with R sub j, the inner product of one of these with a similar representation, the indices k replaced with I and then j, would produce something like this. I want to make sure that these are unit vectors and that all these inner products are 0 when I and j are different. I leave as an exercise the proof that the orthogonality claim holds. It's a straightforward exercise. The observation that these are unit vectors, of course they're unit vectors. We've taken the vector component and divided it out as norm. So we've normalized by having these denominators in there. Think in terms of magnitudes and directions. R1 contains the direction of S1. R2 takes S2, subtracts away the component of it that might be in the direction of S1, and then normalizes that. R3 is based on taking S3, subtracting off the projection of S3 on the span of S1 and S2. So S1 and S2 may contain a couple of directions. We've picked up this new vector. This new vector might have a component in the direction of the first two vectors, subtract it off. By so doing, you bend that new vector until it's orthogonal to the other two. That's how you produce R3 and then normalize it to make it a unit vector. Usual argument for the Gram-Schmidt process, but very much geometry, and we're getting all this geometry because we're in a Hilbert space with a Schauder basis. So things are really working out well in Hilbert spaces with Schauder bases. So the Gram-Schmidt process, just like in Rn, lets you produce an orthonormal basis from a regular old basis. A couple more results, then we'll take a break on the video. Says if R is an orthonormal basis for a Hilbert space H, and if lowercase h is any vector in that Hilbert space, then lowercase h can be written in this form. Sum from k equals 1 to infinity of the inner product of h with r sub k times vector r sub k. Why do you want orthonormal bases so badly? Because finding coefficients in a representation is easy. You just take inner products. It's the orthonormality that allowed that. If you had an orthogonal basis, this wouldn't be too bad. We'd have to deal with the fact that the vectors r sub k might not be unit vectors, and it would become a bit more complicated. If we didn't even have an orthogonal basis, then it's just going to be a mess. That's where the Gram-Schmidt process comes in to clean up that mess. So the claim is that, for one thing, this is a basis in the sense of Schauder, which means every vector can be written as an infinite linear combination, a series of these r sub k's. And the coefficients in that series, they're easy to find. They're easy to find because you have an orthonormal basis. So that's why you want an orthonormal basis. Let's look at Theorem 5.4. 4.5. And the claim is, this is what we get for the representation with respect to this orthonormal basis for vector H. First, Bessel's inequality. Let's run back and look at Bessel's inequality. The claim is, if we had this kind of representation, the claim is if the R sub k's were an orthonormal basis, I think it's an orthogonal set is what we had. And we looked at the sum of the absolute value or modulus of these inner products squared that was less than or equal to H. The H occurs here and here, and the R sub k's come from, I think it was an orthonormal set. Let's look back at Bessel's inequality. I just happen to have it sitting around back here. Here's Bessel's inequality. Yeah, orthonormal set of vectors V in an inner product space. U is any vector in that space. Then the norm squared of U is greater than or equal to the sum from 1 to n. So notice it's a finite sum. That's all we get from Bessel's inequality of the modulus of the inner product squared. So this is exactly what we said. Notice Bessel's inequality is a corollary. Yeah, it's a corollary to the Pythagorean theorem, by the way. So Bessel's inequality gives us, back to here, Bessel's inequality gives us exactly that. Norm of the vector squared is greater than or equal to this finite sum of squares of moduli of inner products. So if we consider S sub n as the sum from k equals 1 to n of the modulus squared of those inner products, this is a sequence. As n varies, we get different terms. It's a monotone sequence. When the index gets bigger, you add more terms in and you pick up more stuff. So it's a monotone increasing sequence. Could be these inner products, some of them are 0. It's maybe not strictly increasing, but monotone means increasing or means non-decreasing. Monotone increasing means non-decreasing. So it either goes up as you increment the index or it stays the same. It doesn't go down. So this is certainly monotone. It's even a positive term sequence. Or non-negative term sequence, I guess I should say. And it's bounded. This sequence, no matter what n is, it's bounded above by the norm of H squared. So we have a monotone bounded sequence of real numbers because we've taken moduli of those inner products. Hey, bounded monotone sequences of real numbers converge. Property from senior level analysis. If it's a convergent sequence, then it's a Cauchy sequence. So we know this sequence converges. Yeah, big deal. That's a sequence of non-negative real numbers. We want to talk about this sequence. So we need to shift gears from this stuff with the coefficients to talk about H sub n, a sum from k equals 1 to n of the inner product of H with R sub k times vector R sub k, a partial sum for this thing here. So we're introducing these H sub n's as partial sums for this series, and we want to show the H sub n's have a limit of H. So consider n greater than m. Without loss of generality, we're showing some Cauchiness here. By the Pythagorean theorem, we know that H sub n minus H sub m, norm squared of, these are both partial sums. We've assumed n is greater than m. So when you subtract off H sub m, you subtract off the first m terms in a partial sum. So the terms we're left with are those for k equals m plus 1 through k equals n, having subtracted off the first m. These are what the terms look like, the H sub n terms. Here's what we get for the difference. We get the norm squared in both cases. Pythagorean theorem says this equals the sum of the moduli squared. It's a finite sum. This is the Pythagorean theorem. A squared plus b squared equals c squared. Kind of writ large. It's for more than just two vectors here. But anyhow, it's the Pythagorean theorem. We've got orthogonality. What's the norm of one of these vectors? Well, the R sub k's have norm 1, so we lose that, and we're just left with a modulus of the inner product, and of course that gets squared by the Pythagorean theorem. So right there is where the Pythagorean theorem is used. So we know this relates to that sequence from the previous slide. This relates to sequences of real numbers. Let me go back to the previous slide. Yeah, this relates to this sequence here. In fact, it relates to the Cauchiness concept for this sequence here. This sequence with these terms converges. So it's Cauchy. Well, if it's Cauchy, then if I were to take S sub n minus S sub m, we get something we could make small by making n and m sufficiently large. In fact, we get this right here. If we took S sub n minus S sub m, we'd get exactly this. If n and m are sufficiently large, since the S sub n sequence is Cauchy, we can make this small. The S sub n sequence is Cauchy. This would represent S sub n minus S sub m. Fine, then you can make this small. If you can make this small by making n and m sufficiently large, then you can make that small. In other words, this sequence, the H sub n sequence, is also a Cauchy sequence, but it's a Cauchy sequence of vectors in H. Hey, H is a Hilbert space, it's complete, Cauchy sequences converge. So that sequence converges to something in H, let's call it H prime. We want to show that it's the H that was introduced at the beginning. But I know it converges to something. Call it H prime. Now, if we'll take H minus H prime, that would be H minus H prime. We've introduced to be the limit of this sequence of partial sums. So it produces a series, but let's leave it at a limit of this form. So that's substitution. H prime is the limit of this sequence of partial sums. We got the R sub I on the right. You can bring that limit out of the inner product. Inner product is continuous. That's an exercise. That's a fact. Inner products are continuous. I forget if it's an exercise or a theorem. I think we stated it as a theorem a few sections back, but it's certainly true. We can bring limits outside of inner products. Now you've got H minus this partial sum, nice finite sum, so we can use properties of partial sums. The R sub k is inner product with R sub I. Well, when you do all this inner product stuff, R sub I with H, one of the inner products, when you do the R sub I inner product with this stuff, you're going to get zeros out because the R sub k and R sub I are orthogonal. Unless k equals I, in which case the inner product's 1. It's the norm squared of R sub I. R sub I is a unit vector. So the orthonormality allows inner products here with the R sub I to simplify down to just the case when k equals I. It's the only one you keep. All the others are associated with inner products of 0. And when k equals I, right there, you get the inner product of H with R sub I. That comes out from here. Here you'd have an R sub I vector, inner product with R sub I. Well, that's 1 because that's the norm squared of a unit vector. So inner product of H with R sub I minus itself, we get 0 out. The only vector, here's a vector, the vector H minus H prime, the only vector that has an inner product of 0 with all of the elements of a basis is the 0 vector. That's left as exercise 8, but it's not too surprising. So it must be that H minus H prime is the 0 vector, and it must be H equals H prime. H prime was represented as this series, so H itself is represented as this series as well. Well, in hindsight, of course, that's the way you dealt with orthonormal bases in linear algebra. You stopped in linear algebra because you're in finite dimensions. So I can excavate out of my linear algebra notes, I'm sure, something that says when you have an orthonormal basis, here's what you get for the linear combination. Here's how you write a arbitrary vector as a linear combination of orthonormal bases. And it's working out just fine here because we're in a Hilbert space with a Schauder basis. That's the place to be. Okay, one last result, and then we'll take a little break on the video. If we have an orthonormal basis, capital R, R1, R2, and so forth, orthonormal basis for a Hilbert space in the sense of Schauder, and we let R sub k be the spans of R1 through R sub k minus 1, as we did in the Graham-Schmidt process. And we'll take H to be an arbitrary vector in the Hilbert space. Then the infimum over S in R sub k, norm of H minus S. Like I said, this is a distance from R sub k to vector H in some settings. This equals the norm of H minus T, where T must take on this form. Right? We know by previous experience there exists a unique vector in that subspace, and this tells you what that vector looks like. It's a partial sum of what we had up here, which is not at all surprising. Maybe a better way of stating this, it's a little less symbolic, but it's a little more conversational. The best approximation of H is given by a partial sum of the orthonormal series. So if you're only going to use the first k minus 1 of the basis vectors to approximate vector H, do so by taking the coefficients as we had them in the previous result. Sometimes these representations are called Fourier series. Fourier series are intimately related to this. I don't see trig functions anywhere. They could be there if we represented things correctly. But we're taking partial sums of these kinds of representations to get best approximations. Well, in reality, we can't deal with infinite things computationally, well, maybe theoretically, but it's useful to approximate and to make these finite approximations. What you want to know is how close is the approximation. We're throwing away an infinite number of terms in making such an approximation. Well, the idea is those terms will be small, and we've got a good finite approximation. So we're not getting into the quality of the approximation overall. Simply, this is the best we can do under these constraints of using these vectors. Proof of this, actually fairly brief. Suppose not. Assume to the contrary that there exists some t prime that's in R sub k. So it's a linear combination of lowercase r sub 1 through lowercase r sub k minus 1. There's some t prime in capital R sub k where the infimum of this quantity equals t prime, and that's strictly less than the norm of h minus t, where t is as described here. So suppose there's a better approximation than that. Well, t prime being in the span of R1 through Rk minus 1 must be some linear combination of R1 through R sub k minus 1. Now, h minus t, norm squared of, okay, h, we know, can be represented as an infinite series of this sort, starting at I equals 1. We subtracted away t. T is a partial sum of that series. So when we take the whole series and subtract this off, when we take h minus t, we take that series and pick up at the kth term. That's why this reads I equals k to infinity. So this is using the previous result, giving us the representation of h in terms of that hypothesized orthonormal basis. Taking the difference produces this. This can be shown. Actually, we'll establish this in Theorem 5.4.7. There'll be a claim made that this is the proper equality. It looks like a giant version of maybe the Pythagorean theorem. That's how it's proved, Pythagorean theorem and limits. Given these are orthonormal vectors, then this equals the sum of the moduli of the coefficient squared. We said something like that earlier, but it was a finite sum and not an infinite sum. But equality holds in the limit as well. So we've got norm of h minus t squared equals this quantity. Let's look at, next, the norm of h minus t prime squared. Well, T prime we've represented as a sum from I equals 1 to k minus 1 of T sub I prime times R sub I. We had a representation of T prime in terms of those R1 through R sub k minus 1 vectors. There it is right there. Let's go back and look at that again. Previous slide. Here it is. Yeah, we had written T prime as a linear combination of R1 through R sub k minus 1 using what I denoted as T sub I primes as the coefficients. So we're substituting that in for T prime. All right, so we've got common terms between H and T prime for R1, R2, up through R sub k minus 1. After that, there are no terms related to the T prime, but there are plenty of terms related to H. So here's the terms for the H vector, taking the difference and collecting together the first k minus 1 orthonormal basis vectors produces this sum here. Here we've got two vectors. So Pythagorean theorem, split it up, then use additional properties of the fact that we have orthonormal vectors here and here. So this is the observation. The equality of this is appropriate with this, as on the previous page. And finite sum here, so we draw this conclusion. It's basically the Pythagorean theorem there as well. This is what we had on the previous slide as the norm of h minus t squared. Sum from k equals 1 to infinity, this norm of h minus t squared. Let's go back and get it. Right. Sum from I equals 1, I equals k to infinity of these inner products was the norm of h minus t squared. So we'll substitute for that norm of h minus t squared. All right, and so what we have then is this stuff plus norm of h minus t squared. Well, this stuff is at least 0 because it's a sum of a bunch of squares of moduli. So this term here is greater than or equal to the norm of h minus t squared. Stringing this together, we've shown that h minus t prime norm squared is greater than or equal to h minus t norm squared. But we got into this by assuming t prime was such that the norm of h minus t prime was less than the norm of h minus t. And this certainly contradicts that. Strictly less than, greater than or equal to. So there's a contradiction. So our original assumption that there is a t prime that's better at approximating h under the conditions described, that's false. And the best approximation is the one that was claimed to be best. And that was a partial sum of what we had seen in Theorem 5.4.5. Okay, so let's take a little break there. Come back later. What's left to be done of primary importance, in my opinion, is showing all infinite dimensional Hilbert spaces with a Schauder basis are the same, or isomorphic. So we'll need to deal a little bit with isomorphisms, and we'll show those are actually all isomorphic to little L2. And that's what we'll call the fundamental theorem of infinite dimensional vector spaces. I can't wait. So I'll see you at the conclusion of section 5.4 here in a little while. Have a nice day.